All right, let's talk about something we all rely on every single day, probably without even thinking about it. We're going to pull back the curtain on the magic that keeps our digital lives private, that invisible shield protecting everything from our DMs to our bank accounts.
I mean, really think about it for a second. Every single time you send an email or buy something online or just message a friend, you're flinging your personal information out across the wild open internet. So, what's stopping the whole world from reading it? Well, that's exactly the puzzle we're going to solve today.
You know, at its heart, this is a really old problem. It's the classic secret message problem. How do you send something from point A to point B and guarantee that only the person at point B can actually understand what you sent? This challenge is basically as old as writing itself.
To pull this off, any secure system needs to nail 3 key things. First up, you need confidentiality. Pretty simple. No one else can snoop on your message. Then you need integrity. That means you have to be sure the message wasn't changed or messed with along the way. And finally, you need authenticity, which is just proof that the sender is really who they claim to be.
Okay, so let's dive into the solution. The oldest, and honestly the most intuitive way to solve this secret message problem is with something called symmetric encryption. Now that name might sound a little techie, but trust me, the idea behind it is incredibly simple.
Picture this. You have a special lockbox. You write your message, pop it inside, and you lock it up with a totally unique key. Then you send the box on its way. The person on the other end needs an identical copy of that same key to open it, and that's it. One single key does both jobs. It locks the box and it unlocks it.
So let's follow a secret message on its journey. It all starts with Alice writing her message. We call this the plain text. Then, she uses that shared secret key to encrypt it, basically turning it into unreadable nonsense that we call ciphertext. This scrambled up message then travels over to Bob, and because Bob has the exact same key, he can use it to decrypt a message, turning it right back into the original plain text. Pretty neat, right?
Now, what's really fascinating is how these locks have evolved. We've gone from really simple secret codes that you could probably solve for fun to digital vaults that are, for all practical purposes, unbreakable. The core idea of one key is still there, but the complexity of the locks, it's gone through the roof.
So on one hand, you have something like the Caesar cipher, the one Julius Caesar supposedly used. It just shifts letters. An A becomes a D, a B becomes an E, and so on. Super easy to crack. But on the other hand, you have modern standards like AES. It uses layers upon layers of really complex math to create what cryptographers call confusion and diffusion. Think of it like this. Confusion makes the relationship between the key and the scrambled text as messy as possible. And diffusion takes one tiny change in your original message and spreads its effect all over the scrambled version. The combination is just digital chaos. No patterns left to find.
And this is where you can really see the mind-blowing difference in security. With that simple Caesar cipher, a bad guy only has, 25 keys to try? You could do that by hand. But for AES 256, the number of possible keys is 2 to the power of 256.
Let me try to put that number into perspective for you. That number is so unbelievably massive, it's bigger than the estimated number of atoms in the entire known universe. So trying to guess the right key, what we call a brute force attack, it's not going to happen. It's completely impossible for any computer we have today or any computer we can even imagine building in the future.
But for all its strength, for all its speed, this one-key system has one big, glaring vulnerability. And it's not the lock itself. It's something much more fundamental.
Exactly. This is the key-sharing dilemma. Alice and Bob both need the exact same key. But how does Alice get the key to Bob without somebody intercepting it? She can't just email it to him because if someone's watching, they'll just grab the key. And then they can open all the secret messages.
And that's the bottom line. This whole process of getting the key from one person to the other, we call it key distribution, is the Achilles heel of the system. The encryption itself can be an unbreakable fortress, but if the key gets stolen on its way to the castle, well, the whole system just falls apart. So we've got this key sharing problem, but now there's a whole new challenge coming over the horizon. One that doesn't just attack the way we share keys, but the lock itself. And that challenge? It's the dawn of quantum computing.
See, quantum computers aren't just faster versions of what we have now. They think in a fundamentally different way. Imagine you're trying to solve a giant maze. A normal computer would try one path, hit a dead end, go back, and try another path, one by one. A quantum computer? It could explore every single path all at the same time. This incredible ability is what gives them the power to crack problems that are completely impossible for today's computers, including our best encryption.
Let's look at the numbers.
A classical computer trying to brute force a standard like AES 128 would need to make about 2 to the power of 128 guesses. That's an impossible number. But a quantum computer could use a special trick called Grover's algorithm, which massively speeds up the search. Instead of checking keys one by one, it's more like checking the square root of that huge number. All of a sudden, breaking the code would only take around 2 to the power of 64 steps. That suddenly takes a never-gonna-happen problem and puts it into the realm of maybe possible.
So what's the plan? Are we all doomed? Well, not exactly. The folks who study this stuff are already way ahead of the game. The first, simplest step is just to use longer keys. Moving up to AES 256 gives us enough security to fend off a quantum attack, at least for now. The next big idea is building what's called crypto-agility, basically designing our security system so we can easily swap in new, stronger algorithms as they're invented. And finally, researchers are already hard at work creating entirely new kinds of encryption that are quantum-proof from the ground up. The race is definitely on.
So, the main thing to take away here is this. Symmetric encryption, this simple idea of one key to both lock and unlock, is the powerful, efficient engine that protects so much of our digital world. It's the invisible workhorse, silently securing massive amounts of our data every single second of every day.
It's a system that has grown from simple letter-swapping games into something of mind-boggling complexity. But with quantum computers looming on the horizon, this age-old cat-and-mouse game between the code makers and the code breakers is about to enter a wild new chapter. And the question really is, are we going to be ready for what comes next?